Hi, this is Dane Quinn from the University of Akron, and for today's video lecture, I would like to talk about imbalance. In particular, I'd like to discuss the vibrations that can arise when you have an unbalanced rotating component in a mechanical system. This is the typical system that we like to discuss. Here we have a frame and a rotating disc, and in particular, that rotating disc has a small mass imbalance. Then that frame is supported by a spring of stiffness K and damping coefficient B, and it basically is constrained to move in here the vertical direction. Now again, that disc has a small imbalance that is given as mu, U for imbalance, that's located a distance r away from the center of rotation. As a result, the mass center of the disk is not at the center of rotation and can provide a source of vibrations for this system. Now, we'll assume that the total mass of the balanced part of the frame and the disk is mf. And then, again, we have this little mass imbalance. Some important characteristics of this system. Well, first, we assume that the disk rotates with constant angular speed. Here, the angle theta describes the orientation of this disk. So the angular speed is theta dot. And again, we're going to assume that theta dot is omega, which is actually constant. Again, we've mentioned the mass imbalance. So the imbalance, which is mu, is a distance of r from the center of rotation. And in particular, the center of rotation is assumed to be the mass center of the frame and disk. So we'll say that's the balanced component. And that has mass mf. And again, that center of rotation is at C. So a little bit about the coordinates that we'll use. The theta is the angle of the disk, and then we assume that x is our coordinate that describes the displacement of the frame. Or the position of the frame with respect to the ground. And likewise, it also describes the displacement of the spring and the damper. So let's evaluate the forces that act on this system. Well, we're going to have three of them, right? We'll have a spring force, right? So we'll say Fs from this elastic piece. We'll have a damping force, Fd, again from the damper. Finally, I have a constraint force from these walls, right? And that we will identify as N, the normal load. Let's look at that just really quickly. If you think about the effect of these walls, from the wall on the left, that can apply a force to the right. The wall on the right, well, that only applies a force directed to the left in the minus I direction. Again, these walls can't pull the frame towards them. They can only keep them from penetrating. Now, when I take these two together, we see that I can have a force in the I direction, either to the right or to the left. I'll combine these into a single force, N, that I assume can act either in the plus I direction, like the force from the left wall, or the minus I direction, like the force from the right wall. So here, this force N serves to constrain the lateral motion. It's a constraint force, so that this frame can only move up and down. Now, as I mentioned earlier, really the important thing for this problem is that the mass center is not at the center of rotation. So the mass center of the entire object, it's offset from the center of rotation, right, at C. So the question is, where is the mass center? Well, we'll calculate that. All right, so let's assume that G is the mass center, and again, I want to know where this point G is. In general, the position of G with respect to O can be determined in the following way. It's the total mass of the system, so that's going to be the mass of the frame plus the mass of the imbalance, times the position of G with respect to some point O, and here I'm not going to specify O yet, but so that has to be equal to really mass times position for all of the individual parts. The individual parts here are the mass of the frame, right, times the position of its mass center, which is C. Again, C is the balanced part of the system, right? So that would be the position of C with respect to O, plus then the position of the imbalance with respect to O. And we'll call this point P for the imbalance. So that's going to be mu times the position of P with respect to O. And this works for any point O. Well, what's a convenient point? Well, you know what? A nice point would be O is equal to C, because the position of C with respect to C is equal to 0, and that drops out. We also have the rest of these nicely described. So here, let's go and identify the direction from C to P as E1. E2 is then the perpendicular direction. And notice that this is oriented by an angle theta from horizontal and vertical. So continuing on, MF plus MU, well, position of G with respect to C. Let's call that rho. And so here, rho is going to be this distance. In the E1 direction. Right? So again, that's the position of the mass center with respect to C. And I don't know what rho is, that's what I'm trying to find. The position of C with respect to C is obviously 0. And then finally, the position of P with respect to C is R in the E1 direction. So here we can solve this for rho. And what we find is that rho is mu, the mass of the imbalance, times the eccentricity of the imbalance, divided by the total mass. Right? So we'll just call that m, where again, m is the total mass, it's m of the frame plus m of the imbalance. And again, remember the frame includes the mass of the balanced part of the disk. This quantity rho is referred to as the eccentricity. And again, it's the distance between the center of rotation and the actual mass center of the system. If the mass imbalance is small relative to the total mass of the system, then the eccentricity is small relative to really how far away that imbalance is located. So for most mechanical systems, we expect them to be relatively well balanced, which means that mu would be small. And as a result, the eccentricity is expected to be small. Really, why do we make such a big deal about where the mass center is? Well, it's because that's what momentum balance needs, right? When we think about momentum balance, it's sum of the forces equals the mass times the acceleration of the mass center. So we have to know the acceleration of the mass center in order to apply momentum balance. And again, the mass center is not located at C, it's offset by some distance. So as this disk rotates relative to the frame, right, the mass center changes position relative to the frame. So we can't describe the acceleration of the mass center simply with x. It's going to be some combination of x and theta. And here I will remind you that theta was this angle, which describes the angular orientation of the mass center. So remember that theta dot was constant. And as a result, the angular acceleration of this disk is, well, in general, theta double dot, but theta dot's constant, so theta double dot is equal to 0. Thinking back to kinematics that, maybe you learned in dynamics or you had a course in kinematics, if I want to find the acceleration of a point on an object relative to another point, I have the following relationship. So the acceleration of g is the acceleration of c plus the angular acceleration of the disk cross the position of g with respect to c plus the angular velocity cross position, omega cross r. So again, this was a relationship that was developed in dynamics. And now we can go and essentially fill in all these details. So what's the acceleration of c? Well, x describes the position of c, x dot would describe the velocity, and as a result, the acceleration of c can be written as x double dot in the j direction. Now, remember that the angular acceleration is 0, and the position of g with respect to c is rho in the E1 direction. Rho was our eccentricity that we found previously. And again, E1 is the direction from c to g. So this term vanishes, right? But this term does not. The angular velocity is omega dot in the k direction. And so that's omega cross, again, rho E1. Okay, we can work all this out. And we end up with, well, again, the acceleration of c. And then finally, this term ends up being minus rho theta dot squared in the E1 direction. Now, I can write this in terms of a single set of directions. And let's choose I and j here, because really the motion of the frame is in the I and j direction. So that requires that we express E1 in the I and j direction. So that's going to be cosine theta in the I direction and sine theta in the j direction. Likewise, E2 would be minus sine I and cosine j. When we go to write this in the I and j direction, well, in the I direction, we have minus rho theta dot squared cosine of theta. In the j direction, we have x double dot minus rho theta dot squared sine theta. Now again, making use of the fact that our angular speed is constant, and in fact we assume that it's known, theta dot is equal to omega. I can integrate this actually and solve for theta. Right? So doing so, we get theta of t is just omega times t. And here I've assumed that theta is equal to 0 at t equals 0. But what that means is that I can actually take this and finally solve for the acceleration. So the acceleration becomes minus rho here is just omega squared cosine omega t in the I direction. and then plus x double dot minus rho omega squared sine omega t in the j direction. What I'll notice from here is that the acceleration of the mass center, right, or of g, is not described with simply x, or the same coordinate used for the forces. And those forces were from the spring and the damper. So finally, let's go and determine the equations of motion. We still need these forces. This was the normal force, which is unknown, right? So I'll write that as n in the I direction. These were from the spring and the damper. So let's go back and remind ourselves of those forces and where they came from. Here, the displacement of the frame is x. We can assume that measures the displacement of the spring and the damper. So the spring force is minus kx in the j direction, and the damping force is minus b times x dot in the j direction. So let's apply linear momentum balance. And again, that is sum of the forces equals mass times acceleration of the mass center. And again, this has to be of the mass center. Can't be just the center of the disk. So, what are the forces? Well, we have n in the I direction. We have the spring force minus kx in the j direction. Damping force minus bx dot in the j direction. And that has to be equal to m. M here is the total mass, which includes the mass of the frame and the mass of the imbalance, times the acceleration. Well, here's the acceleration. So let's write that again. Minus rho omega squared cosine omega t in the I direction, and then x double dot minus rho omega squared sine omega t in the j direction. I can now take components. So in the I direction, we find that on the left side we get n, and from the right side, minus m rho omega squared cosine omega t. So this is the normal force. The normal force fluctuates in time because cosine varies in time. The amplitude of the normal force scales like the frequency squared. So as this rotates faster and faster, this normal load increases in magnitude. What about the j direction? Well, the forces are minus kx minus b x dot, and then equals m times the acceleration in the j direction, which is x double dot minus rho omega squared sine omega t. This provides our equation of motion, which we can now simplify to the following. Let's bring everything in terms of x on the left side, and the rest is on the right side. So we end up with mx double dot plus bx dot plus kx, I kind of multiply through by -1 to make these positive, is equal to m rho omega squared sine omega t. So we have a spring mass damper system, and we have forcing that now arises from the imbalance. Now, this looks very similar to our base excitation problem. Let me remind you what that was. So here, in terms of our relative displacement z, we obtain the equations for base excitation as mz double dot plus b times z dot plus k times z is equal to m u naught. Here u naught is the amplitude of the base motion. Omega squared is the frequency of the base motion. And sine omega t. So if we look, these equations are identical for rotating imbalance and base excitation. I mean, really the only difference is I've chosen to use a different letter for the coordinates. The amplitude of the forcing, both of these depend on the square of the forcing frequency. Right here, rho is the eccentricity, and u naught is the amplitude of the base motion. But again, they play the same role. We even have sine omega t in both. So in both of these cases, the amplitude of the forcing depends on the square of the forcing frequency. And we've already done a lecture that really described the response of systems that take this form. So both of these are examples of frequency squared excitation. And again, that general solution can be used in either case. So again, this frequency squared excitation, really it arises because the acceleration of the component, in this case the block, or the acceleration of the mass center, is measured in a slightly different way than the forces themselves. Here, the forces were determined by the relative displacement, and here the displacement of the frame relative to the ground. But they both lead to identical equations for the response. So that's it. Thanks a lot. Always looking for feedback and comments. Please leave me a message, send me an email. There are lots of ways to get in touch with me. Thanks a lot. Take care. Bye.